Now that we've defined convex functions, let's talk about how we can think of a function being convex based on maybe its components being convex. Maybe we have a complicated function that is combinations of simpler functions. And it'd be nice if we could use basic properties to show that that was convex. So what do you think we could do? Do you think we could say that the sum of convex functions is convex? Do you think we could say that a scalar times a convex function is still convex? Do you think the product of convex functions would still be convex? How about the max of convex functions? Or how about a convex function of a convex function? So what I suggest you do is go to Desmos, for example, or just take out a piece of paper and pencil and try putting in two convex functions and their sum and see if that looks convex. See if you can find a counterexample, because just because it works once doesn't mean it always works, right? So give that a try, pause the video while you do that, and then come on back. Okay, welcome back. Let's go to Desmos. Like I said, let's put in a function like x minus 3 squared, and then let's put in x minus 7 squared. So there's two convex functions. What do you think their sum will look like? This is something that I really had to retrain my intuition on once upon a time, and pretty much have to do every time I think about it. I always think of this, what if we like move them further apart to like, how about 13? I always think that I'm going to have like a bump here and then it'll go up, and then another bump here and then it'll go up again when I add these functions. But let's see what happens when we actually add them. It's not visible on the screen. Well, that's what we get when we add them, that green curve there. Let's turn it black, which looks like a convex function. Now, if you think about the algebra of it, it's probably not surprising that a parabola plus a parabola gives another parabola, rather than having a bump and then an in-between start part and then another bump. Thinking about, just you got an x squared here, you got an x squared there, you're not going to get any x cubed or x to the fourth terms. So from that point of view, it's not surprising, but just looking at the plain old picture, I always think I'm going to get more than one bump in that sum. What about absolute value? We could just take the absolute value of here and here. Absolute value does not tend to be as tall as squaring, huh? And what do you think we'll get when we take the absolute value, the sum of the absolute values? Yeah, well, what would you say? Is that a convex function, that black curve there? Well, it certainly doesn't have any like dip, bump, and dip again. So we'll talk more about whether we want to call that a convex function later. What else do we want to check? A scalar times a convex function. So we could say, let's get rid of this one. How about some scalar times that? I'll have a slider, and yeah, it just makes the convex function vertically magnified, right? Still convex. Oh, wait a minute. Now it's not convex anymore, it's concave. So what would you need to say about a scalar times a convex function for it to still be convex? So think about that. Another thing to think about is the max of convex functions. That gets a little tricky. Let's try f of x equals x minus 3 squared, and then g of x equals x minus 7 squared. What do you think we'll get if we take the max of these two functions? So that says at every point, show us that the max will be whichever of the two y values of those functions is larger. So we'll do that, and we'll give that a different color. So is that a convex function? That blue dotted function there, convex? Sure looks like it. Does this prove that the max is always convex for two convex functions? No, it's just a single example. Could you use the definition of convex function to prove that the max is convex? You probably could if you're a pure math loving kind of person, or could become one if you don't, if you aren't already. Let's do another example here. Let's do something like 0.7x and something like 3x minus 5. Yeah, that's good. So we've got a flat line here and a flat line here, and then the max of those two is this blue path, which is a piecewise linear function. So would you call that convex or concave up? This actually happens in one of the problems we did way back earlier in the semester, the Sailco problem, and we'll talk about that in a video later in our talk today. Let's see, what haven't we tried? Oh, we didn't try product of convex functions. We can certainly try that. What if we just do f of x times g of x? Yeah, it certainly looks concave up to me. But, you know, here we're using linear functions. Sometimes things magically work for linear functions and don't work for nonlinear functions. So let's try throwing in a nonlinearity. Now I have a concave up function, and, well, we haven't said if that's concave up or not. Here's two concave up functions, and their product is not concave up. So apparently products of concave up functions aren't always concave up. Another way to think about this in more variables is that if I just do f of x and y equals x times y, then in the first quadrant, that's all positive because x and y are positive. In the third quadrant, that's all positive because x and y are both negative. But in the second and fourth, it's all negative, so it's a hyperbolic paraboloid, which is not concave up. So a little bit of multidimensional thinking is good every now and then. So just to summarize the answers here, the sum of convex functions is always convex. A scalar times convex function is convex if the scalar is positive, then it's concave if the scalar is negative. Product of convex functions not guaranteed to be anything. Max of convex functions is convex. How about for concave functions? Turns out then, think about it, the min, because everything is upside down, is then concave. And a convex function of a convex function is convex if the outer function here is also non-decreasing, in addition to being convex. So some other problems you can think about. Can we use these properties to talk about whether this sum of absolute residuals is convex? Is the sum of squared residuals convex? How about binary logistic regression? Is that convex in the parameters that we're using? It turns out it is, and here's a proof of it. It takes a bit more doing than you would hope. Yet, when I teach my classes about like shifting left and right and horizontal scaling and stuff, we often use this where we take x values, shift them left and right, and then multiply by horizontal scaling. And that's great for intuition, but it turns out the objective function ends up not convex. So the way you express a linear function this way or in a linear combination can actually make a difference as to whether the overall function is convex or not. The one way you could say that this isn't convex is we end up multiplying a decision variable by another decision variable, kind of like x times y before. Here's a question, is 1 over x convex for practical purposes? Well, if you just think about it, graphing, you've got this part of the hyperbola and that part of the hyperbola, but for a lot of practical problems, x is constrained to be non-negative or maybe even positive. So a function that's not entirely convex might be convex on the feasible region, and then you could say, yes, this is convex enough for what I'm doing. Next, we'll talk about how the Hessian relates to convexity.